problems. Okay, I will present the highlights from the LHCb experiment, and first I would like to thank the organizers for having me here and also for doing an excellent job, I think, with PHENO 2020. Now, let me start with introducing the LHCb detector, which is a forward arm spectrometer designed for precision measurements in the forward region. We have a vertex locator surrounding the interaction region, and together with the tracking stations in front and behind of the magnet station, it provides excellent vertexing and tracking. Then we have particle identification provided by the rich detectors here, the muon stations and the calorimeters. And what is special about LHCb is that we are running at constant number of interactions, constant number of mu, which gives us very stable running conditions and a very stable trigger. This is the data sets that I will talk about. We have collected in total about 9 inverse femtobarn of PP collisions at 7, 8, and 13 TeV, plus various data sets of proton-lead and lead-lead collisions, as well as fixed target data sets. And if I have time, I will comment on one of these results in the very end. I would like to summarize LHCb, the detector, as a multi-purpose detector in the forward region. Of course, we have excellent results for indirect searches for new physics at the multi-TeV scales, mainly through the case of beauty and charm hadrons and by investigating CP violation. But we also have many results testing QCD, and just as an example, I will show today results on pentaquark states, but there is much more. And finally, we have a very ambitious heavy ion program testing quark-gluon plasma and cold nuclear effects. So I would like to start physics-wise presenting a few charm results. And starting with the highlight of last year, one of the highlights of last year, CP violation in charm. LHCb is a charm factory with billions of charm decays, so it's natural to look for CP violation in charm at LHCb. Looking at CP violation in charm is complementary to studies in kaon and P systems where CP violation is well established, because it probes, contrary to kaon and P, it probes the up quark sector. In the standard model, CP violation is expected to be very small, at the order of 10 to the minus 3, 10 to minus 4. Therefore, systematic uncertainties need to be controlled at this level. So what we are measuring is the time-dependent CP asymmetry of the decay rate of a D decaying into final state F minus D bar to the final state F divided by the sum. And this asymmetry receives contribution from direct CP violation and indirect CP violation via mixing or in the interference between mixing and the decay. So we have taken run 2 measurement, 6 inverse femtobarn, and basically the measurement comes down to counting how many D0s or anti-D0s decay into the final state pi or kk, which was taken by LHCb. So we are measuring the rho asymmetry, the number of Ds decaying into the final state minus number of anti-Ds decaying into the final state. And we are taking the initial flavor of the D meson by either taking the charge of the pion in case of prompt decays or the muon charge in case of secondary production. What you see here is the invariant mass distribution D0 pi, or the D0 in case of the secondary production. And you see generally it is a very clean analysis. So the rho asymmetry receives contribution from the CP asymmetry that we want to test. Plus, in addition, we have detector asymmetries from the final state or the muon and the pion tech and production asymmetry. And if you want to measure the CP asymmetry, we need to control these at a level of 10 to minus 3, 10 to minus 4. So in order to reach this sensitivity, we take the difference in rho asymmetries, because then many uncertainties cancel at first order. So what we are measuring is delta ACP, which is the difference between the rho asymmetry of the kk final state minus the pi final state. And the plots below show the invariant mass distribution of kk on the left and pi on the right. You see the signal is clearly dominating, and we have the various background contributions here. So this is the result. We observed CP violation, delta ACP of the order of 10 to minus 4, minus 18.2, minus 9 for the muon tag, which is compatible with previous LHCb results and also with the world average. If we combine this result with the run 1 result, we get delta ACP is minus 15.4 plus minus 2.9 times 10 to the minus 4, which is comparable 5.3 sigma different from 0. It's roughly compatible with the standard model prediction. So this plot here shows the direct CP ACP, and this is the indirect ACP. This is the new LHCb result here, and this is the world average. So if you use LHCb input on the indirect CP violation contribution, we get a measurement of the direct delta the ACP, which is minus 15.7 times 10 to the minus 4. Therefore, this result is clearly dominated by the direct CP violation. So as a summary, this measurement opens a new window to investigate matter-antimatter asymmetry. So as we have seen, we need to, in order to measure the direct CP violation, we need the indirect contribution from the indirect CP violation in mixing and interference. And we measure this, the parameter A gamma, in the same decay channels, D0 to KK and D0 to pi pi. So this is measurement of the time dependence asymmetry, and shown here is the raw asymmetry as a function of the decay time for the KK and for the pi pi channel. So this is the measurement, and if we assume universality and combine it with the previous LHCb result, we get the best result here, A gamma minus 2.9 plus minus 2 times 10 to the minus 4. So as a summary here, we have no indication for CP violation in mixing or interference. And it's at the level of 10 to minus 4, and the standard model prediction is at the level of 10 to minus 5. So even if we analyze the full run 2 data set, we are still statistically limited and far off the standard model prediction. So we need the upgrade 2 of LHCb to reach the sensitivity of the standard model. Then we have a new measurement of oscillation of germ mesons in D0 to K short pi pi decays. So neutral flavored mesons can oscillate between their particle and antiparticle states because the physical mass eigenstates are linear combination of the weak eigenstates. So the mixing parameters are defined as XCP, the normalized mass difference between the mass eigenstates, and YCP, the normalized decay width difference. And in the standard model, X is expected to be very small for germ mesons, but we can enhance it by the presence of new particles. Now, the plot here on the right shows the very high statistics that we have. We have yields of 1.3 million for prompt germ decays and secondary 1 million decays here. And this shows the decay time integrated distribution of this decay in the David's plane. We performed model independent analysis using the so-called Pinflip method. This method is optimized for precision measurement in X, and allowing for CP violation in mixing or interference, we get the following parameters for X and Y. This is also shown in this plane here. This plane here on top right shows in the plane X and Y the uncertainties on the knowledge of X and Y. In blue, it's the world average before the LHCb result was included, and the reddish area gives the world average, including the LHCb measurement. And we can clearly see that the uncertainty in X significantly shrank. This is also visible if you look at the plane of the CP violation parameters phi and Q over P. On the bottom here, we have the new world average, which for the first time provides evidence of a positive mass difference between the neutral germ mesons of X 3.9 plus minus 1 times 10 to the minus 3. And finally, in the charm sector, this is a very new result. It has been shown yesterday for the first time, a search for 25 rare and forbidden decays of D+ and DS mesons. These include for rare charm decays here, then weak annihilation decays, lepton flavor violating mode, and this mode here where you have 2 positive leptons here. All the channels have been normalized and calibrated with the high statistics channel DS to pi phi, and all the channels are well described by background only. I just chose 2 of these channels, and these are background contributions, and we have no evidence for a signal whatsoever. So we have limits. All the limits are given in the backup. These 2 plots show the limits for D+ on the left and the DS on the right. And just to help understanding, the green line gives the previous world best limits. So we can see for several channels, 23, we have the world best limits and significant improvement in the limits. Moving on to precision measurements in beauty, where I have 4 recent results I would like to show. The first one is BS mixing phase phi s from the decay BS to Shay psi kk and BS to Shay psi pi pi. So what we are measuring is the phase difference between the process that the BS directly decays into the final state F and decay via mixing. And in the standard model, this phase phi s is predicted to be 36.8 millirad, but it's highly sensitive to new physics contribution. By choosing these 2 channels with the Shay psi, we assure to have a very high yield and a very clean signature. So we expect to have high precision measurements from these 2 decays. The flavor in this case is tagged from the decay of the other B hadron in the event, and we used part of the run 2 data for this analysis. Combined with the run 1 data, we get phi s minus 41 plus minus 25 millirad. This is well in agreement with the standard model expectation. And the H-fluff combination gives minus 55 plus minus 21 millirad. The plot here shows phi s and delta gamma s plane. This is the green one is the LHCb result, comparable in precision with the Atlas result. This is CMS CDF, and the 0, and this is the standard model prediction. Then rare decays are, of course, an excellent probe for new physics, as heavy particles can enter loop or at tree level. And I would like to discuss a few results on flavor-changing neutral current decays B to SLL transitions. These are forbidden at tree level in the standard model, hence the branch interaction is of the order of 10 to minus 7 and 10 to minus 6. We have several measurements here where we observed a coherent set of discrepancies over the past years. So first, we can look at branching fractions. We can look at angular distributions, and we can also test lepton flavor universality by looking at decays with leptons in the final state. So in this case, having the ratio of decays with muon in the final state over electrons in the final state. So I will discuss 2 of these results here. Let me start with tests of lepton universality. This is the ratio RK and RK star. So this is the branching fraction of B to K star mu mu over B to K star EE. This is theoretically very clean. It should be 1 with very small corrections due to the lepton mass and QED corrections. And this was the run 1 result. It's an old result. In black, it's the result from LHCb, RK and RK star, and you can see in both cases, the LHCb result is below 1 and below the standard model predictions here in color. So this caused a lot of attention, and we have recently published a new measurement of RK with including run 2 data. And in order to reduce systematic effects, we measure R as a double ratio to the resonant channel B to K J psi, and J psi decaying into 2 muons or 2 electrons. This reduces a lot of systematic uncertainties, also due to differences between the electrons and the muons. Because this is very important for LHCb, because electrons are intrinsically difficult to measure at LHCb. First, the trigger threshold is higher for the electrons, so we have less statistics. And secondly, we are suffering from Bremsstrahlung, and sometimes the Bremsstrahlungsphoton is reconstructed together with the electron, and sometimes it's a separate cluster. So it's experimentally a bit tricky to handle. And that's also what you see here in these plots. You see here on the left, the two left plots are the decay channels into 2 muons, and on the right it's the electron. Top is the signal channel, the rare signal channel, bottom is the normalization channel with a J psi. And you can already see here that obviously the muon channel is much cleaner than the electron channels. There is combinatorial background entering and partial reconstructed background, but also the mass resolution is worse for the electron. And third, the statistics is lower. So for the measurement of RK, we get this ratio from a simultaneous fit to the mass of the signal and the normalization channel. And this is the result. RK is 0.846, dominated by the statistical uncertainty. And it's easier to see here in this plot, where we show RK as a function of Q squared, which is the invariant mass of the 2 leptons. The black one is the new measurement by LHCb, with significantly smaller uncertainties than the measurement before. This is the gray area. It came a bit closer to the standard model value. It's 2.5 sigma away from the standard model prediction. So the conclusion is that we cannot conclude on this discrepancy. We need more data. We have to include the 2017 and 2018 data, which will double the statistics here. And we have just recently released another test of lepton universality, the first test of lepton universality with B baryons, by looking at the decay lambda B to proton, kaon, and 2 leptons. And in this case, we got a ratio RPK of 0.86 with quite a large statistical uncertainties of 0.14. So this is compatible with unity within 1 sigma, but the deviation from 1 goes into the same direction. Other measurements are in preparation, especially the update of RK star. The second analysis in this context I would like to present is the angular analysis of rare decays, B to K star mu mu. We measure this as a function of Q squared and the 3 helicity angles which are defined here. So this gives us a large set of variables with reduced series uncertainties. And from these variables, we can construct optimized angular variables where form factors cancel at first order. And one of these variables is the famous P5 prime. This is again an old result where we show P5 prime as a function of Q squared. In black is the LHCb data. Then we have other experiments entering Bell and Atlas and CMS. And what we see, a consistent deviation of the data, it's slightly higher than the standard model prediction here in orange. The observation by LHCb is a tension with the standard model prediction by about 3.4 sigma, but it has also been mentioned that there is a limited theoretical understanding on the effects of, for example, charm loops. The new analysis is updated with 2016 data, and this is the new result, the black one. And we still see consistently that the LHCb data is above the prediction. So the tension is slightly lower. It's 2.5 sigma in the first pin and almost 3 sigma in the second pin here. Also here we have to conclude that the result is not really conclusive. We have to wait for the update with the full run 2 data, which is ongoing. On the next two slides, I will show searches for lepton flavor violating decays. First one is BS to tau mu. This is a very interesting channel to look for lepton flavor violation because in standard model it's highly suppressed. It's of the branching fraction of the order of 10 to the minus 54. The tau is reconstructed as a three-prong, and then I should mention that the new physics models can enhance this branching fraction up to an order of 10 to the minus 8, 10 to the minus 5. So it's a very interesting channel to look for this decay. We have not observed a signal, so we put limits, and the limits are of the order of 10 to the minus 5. So you see, we are entering the region that is interesting for the new physics models. The next channel we were looking at is B to K mu E. And this is interesting for new physics models, including leptoquark or CP violation in the neutrino sector. And these models would predict branching fractions of the order of 10 to minus 8, 10 to minus 10. Again, no signal was observed in the full run 1 data set. So the limits are set at the order of 10 to minus 9. So we are in the region of the new physics models, and also worth mentioning that these limits have been improved by more than an order of magnitude. And recently we have released another search for the decay of B plus to K plus mu tau, setting a limit of 10 to the minus 5, which is comparable to the world best limits. Moving on to spectroscopy. I would like to start with a very recent result of the observation of new Xi baryons decaying into lambda C K minus. Shown here is the invariant mass distribution lambda CK with the masses of the lambda C and the K unsubtracted. And we can nicely see these 3 peaks here in the fit. The masses of these new states are listed, and also the widths are listed here on the right. And there is a large theoretical interest in a study of these baryons with a heavy quark inside to understand the quark binding in the baryons. So what is interesting about this result is that the mass difference to the excited omega C states is about 125 MeV. And this is comparable to the mass difference of omega C to Xi C and Xi C to sigma C, which is also about 125 MeV. And this suggests that these states could be excited Xi C baryons. Of course, this awaits a further analysis. A measurement of the spin parities is needed to confirm whether these are really belong to the same flavor multiplets. Then we have a first observation of excited omega B states in the full data set. For this, we took a very pure sample of Xi B decaying into Xi C and a pion and combined this with a kaon. And the invariant mass distribution is shown here. And for the right sign candidates, we can see these 4 narrow resonances, which have local significances of 3.6 to 7.2 sigma and global significances of 2 to 6 sigma. It's worth noting that the uncertainties are dominated by the uncertainties on the systematic uncertainties on the Xi B mass. Then moving on to the pentaquarks, short history on the pentaquarks. The first pentaquarks were observed by LHCb 4 years ago using the decay channel lambda B to Psi K proton. And the invariant mass distribution of the Psi proton is shown here. And we have this broad resonance here, which was identified as a pentaquark candidate, and this narrow resonance here, pentaquark 4450. Now, there is a large theoretical interest in these states, in trying to understand the nature of these new states, especially trying to find out whether these are tightly bound 5 quark states or loosely bound, more molecular-like states. So we have performed a new measurement using 250,000 candidates, very large statistic sample. And what we see is a new resonance here, a narrow resonance at 4450. And the broad resonance, which was observed before, could be resolved as two narrow resonances here with more than 5 sigma. So the minimum quark content of these states is DUUCC. And what I would like to point out that these states are very close to the mass threshold of sigma CD0 and sigma CD star. So this is a very important result and might shed light on the nature of these exotic states. And since I have a little bit of time, I will quickly show one heavy ion result, which is charm production in fixed target collisions. And LHCb is able to perform fixed target measurements because we have, in order to precisely measure the luminosity, we have a tool to inject gas in the interaction region, and we can therefore measure collisions of the proton beams with these gas molecules. So these points here show the interaction of beam 1 with the gas molecules, and the red one is beam 2 with the gas molecules, and this is the interaction region here in the center. So this is very interesting and provides many measurements that are interesting for cosmic ray physicists. In this case, we performed the first measurement of charm production, Psi and D0, in proton-argon and proton-helium collisions. And especially proton-helium collision is interesting because it's sensitive to very large Bjorken X up to 0.37, and can therefore test whether there is intrinsic charm. The plots here on the bottom show the function, the cross-section of the D0 as a function of the center of mass rapidity. And if there was a significant contribution from intrinsic charm at high X, we would expect to see a deviation, we would expect to see a deviation here at large rapidities. We compare the measurement to predictions without intrinsic charm, and since we don't see a large deviation, we have no evidence for valence-like charm at high X. And then, before I finish, let's come back to the detector. Right now, LHCb is going through an upgrade. Well, unfortunately, it stopped at the moment, but it will ungo as soon as CERN will restart. So LHCb will remove the hardware trigger, so all the detectors will be read out at 30 megahertz for the next run, which means that all the readout systems need to be replaced for all the detectors. Furthermore, we have new optics and photodetectors for the rich detectors and a completely new tracking system with higher granularity. So this will be a new detector for run 3. These plots show upgrade work in progress, removing the old detectors, removing the beam pipe, dismantling some of the detectors, testing the new detectors, setting up the test facilities, and also an event builder prototype. Looking further away, upgrade 2, LHCb is planning for an upgrade 2 for the 2030s. So we plan to have another consolidation upgrade in LS3, and then a large upgrade 2 in LS4. And the intention is the aim is to collect 300 inverse femtobarn in run 5, which means a factor of 10 with respect to upgrade 1. LHCb is well underway. We have green light from the LHCC to proceed to the TDRs, which are expected to be out late 2020. And what can be expected from the upgraded LHCb in the 2030s is visualized here. We see here a CKM triangle with the specific measurements and their uncertainties situation as it is now, and what we can expect here with 300 inverse femtoburns in 10, 15 years from now. So this brings me to my conclusions. There are plenty of interesting results still to come from LHCb run 1, but mainly from run 2 and the combination of the two. And the LHCb upgrade will open the door to many improvements in precision, especially in tracking, but also in statistics because of the better triggering. So interesting times are ahead of us. I will not go through this, all of this, but I would like to point you to the parallel talks of this afternoon. One talk at the 2:15 on search for rare B decays with LHCb, and then followed by a first measurement of isospin amplitudes in lambda B and psi B decays. Thank you.
Thanks, Katharina, and for the very nice talk. There is a question in the Q&A session, and it's from Carlos Wagner. You mentioned the possible impact of tram loop in the determination of P5 prime. Have there been any attempt of estimating how large those effects could be? And also, when will RK star be updated?
Okay, the first one, there are attempts to estimate this. The problem is that the uncertainties are still quite large, but there are also attempts to estimate it from data. So maybe I can comment on this, or I can find a slide on this for the session, for the question session after in the lunch break. I just take a note that I try to find a slide on this, because there are many ideas on how to overcome this, because this is really a large theoretical uncertainty here. And the question on RK star, we tend to say in the next months, and we try very hard to have it out for summer. But it's it sounds like a simple measurement, taking the ratio and the systematic uncertainties cancel. But there are so many tiny details to be understood. It's coming. That's the only thing I can promise, but I can't give a date.